right, Algebra 3. Welcome back for day 2 notes for chapter 4. So day 1 was all about exponents, and today what we're going to be looking at are radicals. And so we're going to focus today on just simple radical form. Again, this is hopefully a great review, but just like exponents, I'm going to start with what does it mean? I'm asking you to look for patterns and then make some kind of conclusion at the end. So we're going to look here again just at what are radicals doing and then what does it mean. So this first one, we have the square root of x squared. And so remember when you are solving problems for x, if you want to undo multiplication, you divide. If you want to undo addition, you subtract. Well, how do you undo an exponent? Well, you square root it. So if you square it, you do a root. And so the square and the 2 power cancel each other out, and you're left with x. Okay? Well, let's take a look at what this one means. This one is x to the 4th. What's the square root of x to the 4th? Well, let's write out what that means. And I'm going to just rewrite x to the 4th. So I know I can rewrite x squared times x squared, because x squared times x squared is x to the 4th. That's what we just found out from day 1. And when I multiply, I can do this. Well, we just now know what that means. This just gives me x times x, which is x squared. So that whole thing gives me x squared. All right, let's take a look at one more thing. We have x to the 6th. Well, x to the 6th can be rewritten, and I'm going to do this a little bit shorthand for you. It can be rewritten as the square root of x squared times the square root of x squared times the square root of x squared. 2, 4, 6. I can rewrite x to the 6th broken up that way. Well, again, I'm going to have x times x times x equals x cubed. Okay, we're going to stop here and we're going to go up to this next row. You guys are going to get to finish the rest here in just a minute. So now let's go to what a cube root means. Well, a cube root means if I have something cubed and I take the cube root of it, the root 3 and the power 3 cancel each other out and you're left with x. That's what it means. Okay, well, let's take a look at what the cube root of x to the 6th means. Well, I'm going to rewrite x to the 6th like this. The cube root of x cubed times the cube root of x cubed equals, oh, the root and the power cancel each other out, and I'm left with x times x. I'm hoping you're starting to see some patterns here. So then let's look at this guy, x to the 9th. Well, x to the 9th can be rewritten as the cube root of x cubed, the cube root of x cubed, and the cube root of x cubed, which gives us x times x times x, which is x cubed. Again, let's look for patterns. All right, we're going to do a couple more, and then you're going to try this on your own. So then we have 4x to the 4th. Well, the 4th root is saying if you raise something to the 4th power, and you want to undo the 4th power, you have to take the 4th root. So the root and the power cancel each other out, and you're left with x. All right, so again, I'm looking at the 4th root. So I need to rewrite things in terms of the 4th root. So this equals x to the 4th times x to the 4th, that's the 4th root, okay, of x to the 4th. Well, you guys just know that the 4th root and the 4th power cancel each other out, and you're left with x times x, which is x squared. All right, last one. You get the 4th root of x to the 12th. Well, I can rewrite x to the 12th like x to the 4th times the 4th root of x to the 4th times the 4th root of x to the 4th, because 4, 8, 12, that's how I rewrite x to the 12th. The root and the power, the root and the power, and the root and the power all cancel each other out. And look at that, we're left with x cubed. Okay, pause the video here and see if you can finish this table. All right, check your work. You should have x to the 4th and x to the 5th. So whenever we ask you to fill in a table like this, what we're really asking you to do is to find the pattern. And hopefully what you were finding was that when you have a power of 15 and a root of 3, what you're doing is you're taking the power divided by the root, and boom, there's your answer of x to the 5th. So let's look at this in a little bit more detail. If I have the 4th root of x to the 20th, what I'm asking you to do is to break down x to the 20th into groups of 4. So I have 5 of them. So 4, okay, we have, there is 8, 16, and then 20 of that, so of x's. So there's my x to the 20th, just broken apart into pieces. You guys already know that the power and the root cancel each other out, and you're left with x times x times x times x times x, which gives us x to the 5th. Now notice, what's 20 divided by 4? There it is, okay? So if you take the power and it divides nicely by the root, then you know you have an answer. So how are we going to use this to do simple radical form? Well, what I'm looking for then are those nice groups of squares or cubes or fourths or whatever root we give you, you're looking for those pieces. So let's take a look at 2 examples. And let me erase these guys. Okay, so let's look at these examples here. Now, you have to break 128 into really nice groups of 4. And the best way to do that is by what's known as prime factorization. Now, prime factorization, the way you were probably taught, looks like this. You take 128 divided by 2, and you get 64. 64 can be divided by 2. And you get 32, so on and so forth, and this is known as the prime factorization tree. If you prefer this method, that is great. Use the prime factorization tree. But what you're trying to do is you're trying to get 128 in terms of all of its factors, prime factors. And so the way I'm going to show you might be a little bit different style. And the reason I do this is because it just, when I do the tree, I get a whole bunch of 2s and 3s, and it's hard, it kind of like spreads out this way, and that's really hard for me to organize my work. So the method I'm going to teach you is exactly the prime method, the prime factorization tree. I just keep it all like lined up so I can see it. So I look at this, I have 128, and I'm going to divide by 2. 128 divided by 2 gives me 64, okay? Well, I keep going. Remember, 2 is our first prime number, so I keep going. So 64 divided by 2 is 32. 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. And 2 divided by 2 is 1. You can stop when you get to 1. That's how you know you're done. Well, now I can see all of my prime factorizations really nice, but notice what I'm looking for. I'm looking to make groups of 4 because I know if I can write something to the 4th power, the 4th root will cancel it out. So all I come over here to do is I circle 1, 2, 3, 4. I circle 2 to the 4th. Now I don't have another 2 to the 4th. I have what's left over here, 2 cubed. So I can only circle groups of 4. All right, so now my job is just to rewrite the 4th root of 128 into pieces. Okay, so I take the 4th root, means I have 2 to the 4th times 2 cubed. Now, if you don't believe me, put that in your calculator. Take 2 to the 4th times 2 cubed, and you're going to see, wow, it's 128. But now, well, here comes the magic, because anything raised to the 4th power gets to leave the radical. It means it gets to escape and it gets to come outside. Remember, we just found out if you take the power divided by the root, 4 divided by 4 means it's a 1. Yes, so that means I get to have this 2 gets to leave jail. So it's like it's get out of free jail card, okay? It gets to leave the radical sign. And so what that means is I have a 2 now on the outside, but does this guy get to leave? No, because what's 3 divided by 4? Is that a nice number? No, it's a fraction. So this doesn't get to leave. This does not cancel out that. And the way we would write that is 2 times, that means times, guys, right there. So that's 2 times the 4th root of 8. And that's as simplified as you're going to get. You cannot pull out another 2. Okay, let's take a look at example 2. So what's the root here? Well, remember, mathematicians are lazy. They're not going to tell you that that's a squared. You have to know it. So I'm looking for groups of 2. So I'm going to do 98. And I do my prime factorization. So I do 98 divided by 2 gives me 49. Oh no, I can't divide by 2. So what's my next prime number? Well, my next prime number is 3. So can I divide 49 by 3? Nope. So what's my next prime number? 5. Can I take 49 divided by 5? Nope. What's my next prime number? Oh, it's 7. Yay, so 7 will work. So 49 divided by 7 is 7. And then I have 7 divided by 7 is 1. I'm done. All right, I'm looking for groups of 2. Well, I only have a group of 2 right there. So now my job is I need to rewrite 98 as groups of 2 and whatever's left over. So I can write 7 squared times 2. Put it in your calculator and see if 7 squared times 2 equals 98. It should. All we're doing is rewriting 98 as its prime factorization. So what gets to leave the jail, okay? What gets to leave the radical? This guy. So we know that a 2 divided by 2 is 1. So that means I get to have 1 7 come to the outside. It escapes, but everything else is left. Again, put that whole thing into your calculator and see if it works. Put in the square root of 98, you'll get a decimal. Then put in 7 times the square root of 2, you should get the same decimal. Okay, try it and see. All right, now it is your turn. Turn your paper over, and I want you guys to try example 3 and example 4. Welcome back, Algebra 3. Check your answers to example 3 and 4. I've put out all of my work there, and make sure you have both of these in reduced form. So now let's look at example 5 and 6, because example 5 and 6 now throw a little bit of a curveball at you. We now have negative numbers. And so I'm going to start here. I'm going to do my thing here where I'm going to divide by 2, and I get 8, and I'm going to get 2. I get 4, divide by 2, and you get 2. 2 divided by 2 is 1. And I'm looking for groups of 3. Okay, so now I have this. I can now say that negative 16 can be rewritten as 2 to the third power times a negative 2. Okay, well, what gets to leave? Well, anything to the third power gets to leave, which means I have a 2 cube root negative 2. And there's my answer. Now you might be questioning this and saying like, can I have the cube root of a negative number? Sure you can. Think about what it takes. And so if you don't believe that, I want you to really look at this guy. Oh, I don't know if you can see it. Put that into your calculator, which you guys cannot see online, I apologize. But if you put this into your calculator, take the cube root of negative 16, okay, when you put that into your calculator, you'll get something like negative 2.5198421. Then put this into your calculator. 2 times the cube root of negative 2, you get that exact same decimal. All right, but the question always is what happens when we start throwing in variables? Well, nothing has changed. We're still writing things in groups of whatever the root is. So I need to rewrite my variable in terms of groups of 4. So now I have to think about y to the 10th. So y to the 10th can be rewritten as y to the 4th times y to the 4th, which is y to the 8th. Now think about how much is left over. Well, I would have 2 left over. So I have 4 plus 4 is 8 plus 2 is 10. So that's how I'm going to break out my y's. So now think about what gets to leave. Anything with the 4th power gets to leave. So this guy gets to leave, and then that guy gets to leave, which means I have y times y all times this. Now I can't simplify anything under the radical, but I can simplify y times y. Y times y is y squared, and you have the 4th root of y squared. No, that looks like a weird answer, but that's it. That is as simplified as it gets. All right, let's take a minute to now practice this skill with both numbers and variables. I'm going to do one, and then I'm going to have you guys try the rest. Okay, so let's look at this next example. Wow, that looks like a crazy amount of work. Well, not really. You have to go back and do 243. So 243 divided by 2 doesn't work, so I start with my next prime, and my next prime is 3. That'll give me 81. 81 divided by 3 is 27. 27 divided by 3, 9. 9 divided by 3 is 3. 3 divided by 3 is 1. And I'm looking for groups of 5. So 1, 2, 3, 4, 5. Ooh, I get to circle that whole thing. That means 243 is a perfect fifth root. So what this means now, I have to rewrite everything in terms of groups of 5. So I would have 3 to the 5th times a to the 5th times a to the 5th times a to the 5th. Notice 15 is 5 plus 5 plus 5. Okay. Now I have times b to the 5th times c to the 5th times c to the 5th. There's 5, 10, 15, 20, 25 times d to the 5th times d to the 5th times d to the 5th times d to the 5th. It's a lot of 5s. So now what gets to come out? Well, look at that. Every single thing gets to come out because everything has a power of 5. So this becomes 3, and I would have 1, 2, 3, a cubed. Now you could have also done our little thing we did at the beginning. 15 divided by 5 is 3. You have 1b. 25 divided by 5 is 1, 2, 3, 4. Oh, 5 c's get to leave, and 4 b's got to leave. Okay. Pause the video here and see if you can finish the last 2 examples. Put the last 2 examples in simple radical form. All right, time to check your answers. Now I've written everything out. You can pause the video here, make sure your work matches mine. But remember, you're just looking for groups that you can remove, okay? This one is a squared root. This one is a 4th root, so I was looking for groups of 2 here. I was looking for groups of 4 there. Thanks for watching the video. Stay tuned for day 3.